Okay, I think I'm online. Hello, guys. My name is Fernando, and I'm going to be your mentor for the deep learning degree. I'm also sharing this link with some of my students in Brazil because I will be presenting a overview of neural networks. So I think this can be helpful for them as well. So first of all, I'll be sharing my screen with you for the entire class. Okay, so here it's the outline of my presentation. First, I will present what's my role for you guys as a mentor. Then I'm going to present some intuitions behind neural networks. Then I'm going to present how the neural networks learn. It's basically the gradient descent method. And finally, I will also present the activation functions, which is also a very important part in neural networks. So let's start. My role as a mentor, it's very similar to what I already provide to the Brazilian mentorship. The only difference is that since it's a small group, you guys can schedule weekly one-to-one calls in this link. It's like 15 minutes calls, and you guys can use those calls either to ask questions to me and also to make a study plan with me. I'll show you an example. What I'm usually doing is like a shared Google Calendar in which I have with the student some timings and some goals, weekly goals. So this is something that you can use. So just keep in mind this link in case you guys are interested. Also, one more role is to conduct weekly webinars with you, which I'm doing right now with relevant content. So every week I will be presenting some content about deep learning, neural networks, basically just a review of what you guys are watching in the nano degree. And also, I'll be like a coach for you guys. I'll be helping you to complete the coursework, to provide technical help. As whenever possible, I want to motivate you guys and also create a community, engaging community over Slack. In Brazil, we use WhatsApp, and internationally, we use Slack. Okay, so that's my role, and I will start with the first presentation, intuitions behind neural networks. I think just... I will start with the first presentation. Put here. Okay, there's some people watching. All right, so let me find the first presentation. Okay, this one. So, intuitions behind neural networks. What I'm going to present here. First, what's a neural network? Then I'll present the perceptron. Then I will add layers to this perceptron. Then some visualizations, and finally a summary. So what's really a neural network? For now, you guys can think as just a giant function that tries to correlate inputs and outputs. For example, in the Titanic disaster, some possible inputs, if you are trying to predict if someone survived or not, could be the age, the gender, and the ticket price. And as output, we could have a binary output of either if the passenger survived or not. For example, in this scatter plot, I have the age and the ticket price, and we can notice that we can draw a decision boundary in order to find out which passenger survived or not. So it's the goal of a neural network to figure out this decision boundary to create a model so that new data points can be classified to either survived or did not survive. So let's dig deeper on what's going on here, understand better how those inputs and outputs are correlated. First of all, we have weights. Those weights are multiplied to the input and they give the importance of each input. We also have a bias, which is a constant value and allows to slide the decision boundary. We will see this in the visualization section. All of those multiplications and sums here, they will be summed here, and then a information is extracted from this sum, which is called activation function. For now, you can think of activation function as something as simple as 1 if positive and 0 if negative. So you basically are trying to make this sum under some specific range. I'll have later one video just to talk about the activation functions. And this model I created here has a name. It's actually called perceptron because basically it mimics the way that the neurons in our brain, basically based on some input signals, it can fire or not a output signal. So let's play a little with this perceptron and see what it can do. If my weight is 1, and with this activation function, basically what's going to do is to have an output 1 if it's positive and output 0 if it's negative. It's not something impressive. Let me show something different. Now my weight has -1, and we can see now the output is being inverted. If I have a -1 as input, the input if I have a negative value as input, the output is 1, and a positive value as input, the output is 0. What I have here is a logical operation. It's the NOT operator, so it's basically inverting the input. Let me show something else. Now I have 2 inputs with those weights, this bias. With those values, what I have here is a OR operator, in which it's going to be 1 only if both inputs are 1. So it's going to be basically 1 plus 1 minus 0.5 is positive, so output is 1. And, or better, the OR operator will be output 1 and if either the first or the second input is 1. I got confused, yeah. So, and it's going to be 0 only if both inputs are 0, because then it should be 0 plus 0 minus 0.5, it's negative, then output is 0. Now, I'm changing just the bias, and just by changing the bias, I have a different operator. I have the AND operator. And now, yeah, as I mentioned before, it's going to be 1 as output only if both inputs are 1. Okay, so, and why am I talking about logical operators here? I'm talking about this because it's interesting that you can find logical correlations. You can teach the weights in a way that we can find out logical relationships between the input and the output. However, the perceptron has a limitation. This limitation is the following. It can only draw linear decision boundaries or straight lines. And as you might guess, linear decision boundaries will not always solve all the possible decision boundaries. For example, I have here a exclusive OR, and for this case, a straight line is not going to split the positive and negative classes. So in order to add more as a solution for nonlinear decision boundaries, we can add more layers to our neural network. Instead of having just one perceptron, we can have many perceptrons connected to each other. So I have here one perceptron, I made a copy, and now I'm connecting them. Now you can see that besides the input and the output, I can also have what's called hidden layers in between. And I actually can have as many hidden layers as I want. And there is a mathematical proof called universal approximation of neural networks that shows that by adding hidden layers and activation functions, we can approximate any function. So by adding layers, we can make our neural network very powerful. And I will simplify this image here, because usually what you're going to see is the neural networks in this way, like some small balls here. So you always have to keep in mind when you see a architecture like this, that we have weights, they're summed, and there is also a activation function being applied before going to the next. Okay, so, and for solving this exclusive OR operator, one possible solution is those are with those weights here. So, but now it's kind of difficult to imagine this. So that's why I have some visualizations here in the end of what we just implemented. First, the AND OR operator. The AND OR operator can be illustrated in this image. And as you can see, when you change the weights, is like changing the slope of the decision boundary. While when you change the bias, it's like sliding the decision boundary. You can see that by changing the bias, I can have either a AND operator or the OR operator. So that's why before I changing to minus 1.5 or minus 0.5, I could change it to AND or OR operator. The exclusive OR, I have here one more hidden layer, and you can see that now the decision boundary allows me to have not just one straight line, but two straight lines. I have actually two regions for the negative classes and one region for the positive classes. So that's how we can visualize the solution of the exclusive OR by using the weights here. And we are not just limited to straight lines. I can actually have very complex decision boundaries. For example, here I'm using the sigmoid activation function for having a more complex decision boundary. And we can then train those weights, adapt those weights in order to fit this decision boundary in our training data. And finally, going back to that Titanic example, this is one possible solution. You can see that by changing those weights, I can find out a decision boundary to fit in this training set. You can see that we don't need a perfect decision boundary. We want a decision boundary that generalizes well between those data points. We don't want to memorize all those data points. Okay, but as you might guess, it would be very difficult to set all of those weights by hand. So they are actually not defined by hand, they are learned automatically. And that's what I'm going to show you in the next video, how the neural networks, they learn those weights. Basically, they actually use just they use optimizers like gradient descent or optimizers based on gradient descent. Okay, so as a summary of this first part, neural networks, they are actually not so complex. They are just a set of multiplications and sums followed by activation functions, which are called here nonlinear operations. And each block of a neural network is a perceptron or a neuron. And by combining them in layers, we can have very complex approximations, and they can learn anything. And finally, deep learning can be defined as the usage of deep neural networks to learn very complex relationships, such as speech recognition or face detection. So that's the first part. And in the next video, in the second part here, I will present how those weights are learned. So I'll just have a water first. Let me close this first video. And yeah. So let's start the second part. So I just presented some weights. Now my goal is to show how does a neural network learn. So present 4 parts. First, why we need to know this. Next, some optimizers, gradient descent, and finally a summary. So as I showed before, a neural network just try to correlate inputs and outputs. As I mentioned, we have weights that they are multiplied to the input, biases that are constant, they are summed, and Bayesian function for the next layer, and then we have output. When we also just seen that by changing the values of those weights, we can have control of the decision boundary of a neural network. But how are those weights learned? That's what I'm going to show you. But first, I want to show you why you need to know this. You need to know this because when you are programming a code with neural networks, this is you will have to define some parameters here, such as optimizer, loss function, and learning rate. And there is and those parameters, they are actually going to define how those weights are being learned. So in short, why you need to know how the weights are learned? You need to know this because when you are coding neural networks, you will need to know this for programming them. So okay, so basically, in short, I'm going to present optimizers, loss function, and learning rate. It's summarized with this. So first of all, optimizers. What are optimizers? Optimizers are methods that seeks to minimize a loss function. What I have here is a loss function. They are also called cost or objective function. So basically, for learning weights, we have to define the weights of the model of our neural network in a way that we can put in a optimizers in a way that it has to be minimized. In other words, we have to define a loss function that its minimum would represent the best model for our neural network. Here I'm comparing different optimizers, and each one has their momentums or their own strategy for trying to find the minimum point, but they usually are always based on the most classical method, which is called gradient descent. Also, I want to show you that those optimizers, they are available on the Keras. If you are programming using Keras, you can choose which optimizer to use here in the documentation. But I'm going to describe here the gradient descent because all other methods are somewhat related to the gradient descent. So in order to show this, first I will have a very simple example here, just with one input and one output. also have just one weight and one bias. You can think as the X as the input, for example, as the area of a house, and the output as the price of a house. And suppose that we want to find a weight and a bias to correlate both. I can also plot this. So the blue data points are some data that we have, and the red line is the prediction that we want to set those weights and bias in order to fit in this data set. So first of all, we, as I said before, in order to use optimizers, we first have to define a loss function in order to minimize the loss function in order to have the best model. So how do we define a loss function for this case here? We have here the function. It's just the function of our model. It's just the function of a straight line. And then in order to define a loss, we first get all of those errors, or the distance between each of those data points and the prediction. Since those distances can be either positive or negative, as I show here, we will get the squared of those distances in order to always have a positive value as our error. And if I take the average of those distances, I will have one possible loss function. This loss function is very popular for regression problems. It's called mean squared error. There are many loss functions. They depend on the type of output that you have. If you have a continuous value, as here, you will be usually using mean squared error. So, and if you go to Keras dash losses, you see other types of loss functions. Depending on the type of output that you have to choose different loss functions to be minimized in your problem. And let me plot here this loss function. So as you can see, it's like a convex function here, in which the minimum would represent the best model for this scenario. So basically, the goal is using iteration to update the weights in order to minimize the loss function. And the minimum of the loss function is the best model. But how this iteration happens, I will illustrate here. But in order to illustrate how this iteration happens, I will remove the bias in this model. Now I can plot in 2 dimensions, where I have the weights here and the loss function in the y-axis. So first of all, the weight is initialized randomly in a point, and we take the loss function in this point. It's worth mentioning that usually the loss function will not be convex like this, but for now, for simplicity, let's assume that the loss function is convex. For us, it's quite obvious where it's the minimum point in this loss function, but for the neural network, if the weight is here, what it can really see is just this region around the loss function. And the information that can be extracted from this region is the slope. So based on the slope, or the inclination of the loss function, also we can call derivatives, or if it is multidimensional, gradient. So based on this information, we can update the weights. How the updates happens? It's actually very simple. You will just take the previous weight and then add a learning rate times this slope. This learning rate we will see later, but basically it's a constant value that you have to set in order to define the speed of in which these weights are going to be updated. We have to be careful with this learning rate, because if it's too big, its value, it can actually never converge to the minimum point. And if you have a very small value, it will take forever and also never converge. So it's good when you're starting to train neural networks to try out different values of learning rate. Okay, so that's all. That's a summary of what's really a gradient descent method or optimizers. So as a summary, the weights from a neural network are learned with optimizers. That's how they are learned. A optimizer, they seeks to minimize a loss function in terms of its weights. As I showed, there are many loss functions. They depend on the type of output that you have. And the minimum of a loss function has the best weights for fitting a neural network. And finally, the learning rate defines how fast or slow it's this minimum search. Okay, so here I finish this second part, and it's now in the third part. It's just missing to present you guys what's activation functions in neural networks. Let me close here. Okay, so activation functions. Here I'll present you guys a motivation as well, then a overview of the main activation functions, some visualizations, a summary, and actually there is no assignment, so I'll finish just with a summary. So a motivation. We've seen that by adding layers in a neural network, I just presented in the first video, we've seen that by adding layers, we can allow the neural network to have more complexity and draw non-linear decision boundaries. However, that's not enough. If we don't use activation functions, even if you are using many hidden layers, if you don't use activation functions, the output will be limited to linear decision boundaries, because you will be basically combining linear methods. So in short, why do we need, in order to answer the question, why do we need activation functions? The answer is because we need them to have non-linear decision boundaries. So a overview. I previously presented that a activation function could be as simple as 1 if positive and 0 if negative. However, this activation function I am showing a plot, it's actually not a good activation function, because as I mentioned in the previous video, in order to learn to update the weights, this is based on the derivative or the slope of this combination of functions. And as you can see here, this function is a flat one, so there is no derivative either here or here. So it would be very difficult to update the weights with this activation function. Instead of this one, there is another one, which is called sigmoid function, which is more popular. As you can see, it has now a derivative, and it ranges from 0 to 1. So this sigmoid function is very popular. And this is the equation of the activation function of the sigmoid. And it's very popular as the output of binary classification problems. In other words, if you want as output a value ranging from 0 to 1, usually you'll be using a sigmoid. Also, for multi-class classification problems, if you have many classes instead of just one, there is a generalization of the sigmoid function, which is called softmax. So, for example, if your output is not either predicting if a picture has a cat or not, instead of this, suppose that your output is to predict the breed of a dog. So you have many classes. So then you'll be using the softmax here. Let me illustrate how the softmax works. So basically, the sum will have different values, and you are going to take the exponential of this sum, then sum all of those exponentials, and divide each of those values to their sum. So this allows you to have a probability distribution. So each of those values are converted to one like confidence probability. So the higher the value, the higher it's going to be this probability. Okay, so as I said, those are activation functions that you'll be using for output of classification problems. However, they are not good for hidden layers. For hidden layers, one popular activation function is the hyperbolic tangent. It is quite superior than the sigmoid because it has 0 as mean. So as I said, it's used usually in hidden layers. That's the equation. And as I said, it has 0 as mean. So it makes it faster than the sigmoid function. However, both of those functions, they have the same problem called vanishing gradient problem. As you can see, for higher values, the derivative is almost 0. So the update of weights would be very slow. And also when propagating those weights for the hidden layers, it would make them, since there are many multiplications, it would make them tend to 0. So there is one other activation function, which is one of the most popular for the hidden layers, which is called ReLU. And what does ReLU do? It is very simple. It will return the very same value if it's positive, and it will cancel any negative value. Negative values will return as 0. It's also always used for hidden layers, and it's faster and computationally cheaper than the hyperbolic tangent, because you don't need to calculate exponentials here. You just have to check if the value is positive, return the very same. Also, its derivative is always 1, so that's why it makes it faster for learning. However, there is also a disadvantage in the ReLU, because based on this value of sums, if it's a negative value, then they can also kill some units in the neural network. They can't be updated anymore. And as a solution for those situations, there is also the leaky ReLU, which also has a slightly inclination here in order to allow also for updates in the negative regions. As you might have noticed here, I'm actually here creating a table with a summary of all the types of activation functions. So I showed here the sigmoid and softmax, that's for output of classification, and those two activation functions here are for the hidden layers. But it's missing one activation function, one situation actually. What about if your output is a regression problem? For regression problem, you actually use the linear or no activation function. In other words, if your output is a continuous value, you actually don't need a activation function. The output will be just the sum of all of those values. So basically, a big summary of what you need to know of activation functions is in this table. You have both plots, their names, and where to use them. So let's have some visualizations to get a better intuition of those activation functions. First of all, I have here, I'm using playground of TensorFlow here. I have a simple architecture with 2 hidden layers, 4 neurons and 2 neurons. And my goal here is to split the blue classes and the orange classes. And I will be comparing different activation functions. So first of all, I'll show how it works if you're using linear or no activation functions. As I mentioned before, if you don't use activation functions or using linear, as you can see, your output will be limited to linear decision boundaries. So actually, then it's like using just one perceptron. You will not actually be using all the power of the hidden layers if you are using a linear activation function. Now, for this very same problem, I'm changing here to the hyperbolic tangent, and you can see that quickly this neural network was able to minimize this training loss and to figure out weights in order to split those 2 classes. And finally, for the ReLU, you can see that it was even quicker than the hyperbolic tangent. And you can also notice that the shape is a little different. For the ReLU, it's like taking multiple nonlinear, combining multiple nonlinear cuts in this decision boundary, while in the hyperbolic tangent is more smooth. Usually, you'll be using the ReLU activation function. There are some cases that the hyperbolic tangent is more superior. If you guys want to try out on Playground, if you use this exclusive R, you will notice that the hyperbolic tangent works better than the ReLU. But usually you will be using ReLU. It should be your first guess, because it's faster and simpler. So, okay, as a summary, the summary is actually just the table that I previously presented. What you need to know about activation functions is that first, for the hidden layers, you'll be choosing either the hyperbolic tangent or the ReLU or leaky ReLU. And for the output of classification problems, you'll be using the sigmoid for binary or the softmax for multi-classification problems. And for the output of regression problems, for the last layer, for the output layer, you don't need to use any activation function. So Yeah, that's all. I don't know how much time went so far, but yeah, that's what I have for presenting to you guys right now. And if you have some question, feel free to ask here in the chat. I will wait a little, and if there are no questions, I'll just finish this first webinar. Actually, there is one question here. I heard that it is better than sigmoid because it doesn't. Yeah, that's also an interesting point. A very long floating point. Yeah, what I heard about this, the hyperbolic tangent, yeah, it was what I mentioned, that the fact that it has zero mean makes it quite superior than the other, than the sigmoid. Also empirically, when trying on playground, it looks quite faster. Uh, any other question? Okay, so thank you for watching, and I hope this video was useful for giving you guys some intuition of neural networks, learning a little about gradient descent, activation functions, and you guys can find me on Slack, or for the Brazilians on WhatsApp. You can find me there for asking questions if necessary. All right, have you guys a great Saturday, and bye-bye.